Well, welcome. It is Thursday night, and we are about to do some great pre-calculus. I'm very much looking forward to tonight. This is my favorite topic. We're talking about rational functions. I have the great Vicky Carter, Tom Dick, and Steve Kokoska here once again. I'm super excited to have them joining us, giving us a little bit of technology help, and Steve giving us a little bit of the pre-cal help and giving us some content knowledge. I'm really excited to see that. I've seen some students already on chatting and asking about the document, so I'll go ahead and address that. It is down here in the description, so if you look down for the link down below, it should be in that description there. You should see the link for the student document. The teacher document will be there tomorrow. At some point, we'll go ahead and have that up there. So no cheating and getting the answers tonight for the live podcast, but if you are watching this back streaming on Friday or at some later date, the teacher document should also be down there. So I will turn it away to Steve, and why don't you take it away for us?
Thank you very much, Curtis. It's great to be back with you and Vicky and Tom. Since this is your favorite topic, Curtis, I guess that means I can ask you a lot of questions.
You
So,
can ask me all the questions you want, Steve. Just don't expect good answers.
okay, all right. All right, well, we've got some good problems tonight, I think, to deal with rational functions. I think Tom and Vicky both have some great calculator stuff to show you, some great calculator functions to show you that will help us understand rational functions. So I'm going to start out with this one. We have this function f defined in the following way. And you'll notice here, the way that I defined f, I actually gave it to you in factored form in both the numerator and the denominator. It might not be given to you that way. You might have to do a little bit of factoring on your own first. One thing before I even go on to any of the questions you might notice about this rational function, you might think a little bit about the degree in the numerator and the degree in the denominator. I think if you look at that and stare at that a little bit, you'll see that the degree in the numerator and the denominator is equal. It's both 4. And that might play a role here later on in some of these other questions. And you might also think about multiplying everything out. You might not have to do that, but if you were to multiply all of that out in the numerator and the denominator, you might think a little bit about what the leading coefficient in the numerator and the denominator might look like. Okay, well, here we go. Let's see if we can find all the real zeros of f. I'm going to arrow down just a little bit if I can. I always have a little trouble doing this. Mark O'Reilly always gives me grief about this, but there we go. We're going to see if we can find all the real zeros of f. Now, I went a little bit too far here in my cancellation, perhaps, but I was looking ahead. The very first thing I thought about for this function is, well, what is the domain? Well, the domain here is of a rational function, and the domain is all reals except where the denominator is 0. So since this is in factored form, and since we have 3 distinct linear factors, the domain is all reals except where x is equal to, well, -1, 2, and -3, because, well, that's what makes these linear factors 0. And I can't have a 0 in the denominator. So that's the first thing I looked at. And now to think about, well, where are the real zeros? Well, I'm going to put a little line here. Yeah, I've got an equal sign there, but I'm going to look to the left of that line for a minute. What I really need to do to decide where the real zeros are is I have to find all the values of x where the numerator is 0 and where the denominator is non-zero. Well, there are 2 places where the numerator is 0. One of them is -1 and the other one is 2. But wait a minute. Neither one of those values is in the domain. Both of those values also make the denominator 0. They're not in the domain. That means, son of a gun, there are no real zeros of this rational function f. Okay, now I went a little bit farther here. I'm going to try this again, see if I can get it. I went a little bit farther. And I tried to simplify this a little bit. I tried to cancel out some like terms. There we go. We arrow up just a little more. How about that? There we go. I canceled out some like terms, and I'm going to be looking at this expression right here. I want to know in part B, find the coordinates of any holes in the graph of f. Well, how do you do that? Well, what I need to do is to cancel out the like terms. And where I cancel out a common factor in both the numerator and the denominator, if that factor is no longer in the denominator, then I have a hole in the graph. And that happens with that factor x minus 2. I've canceled one of them. It's no longer in the denominator. It's no longer part of that product in the denominator. And that tells me that I have a hole in the graph at x equal 2. Now, one issue is, well, how do I know that that y coordinate is 0? How do I know that's where the hole is? Well, bluntly, what I do is I take that x value of 2 and I plug it in to that reduced expression right here. And I've got a 2 in the, pardon me, I've got a 0 in the numerator and something non-zero in the denominator. So the value is 0. So that tells me finally there's a hole in the graph at 2, 0. Okay, where are the vertical asymptotes? Well, let's see. I look at my cancellation. I do all the cancellation that I can, all the linear factors. And any linear factor that's left in the denominator, well, that's going to lead me to a vertical asymptote. So I have an x plus 1 left in the denominator. I have an x plus 3 left in the denominator. The zeros of those two linear factors are minus 1 and minus 3. I know that I have a vertical asymptote at those two values. Terrific. And finally, well, almost finally, I need two mathematical expressions that describe the end behavior of f. Well, okay, Curtis, I need a little help here.
All
How the
right.
devil did I get those two mathematical expressions? The limit as x goes to infinity of f of x is 1. That is, as x increases without bound, the value of the function is getting closer and closer to 1. As x decreases without bound, the value of the function is also getting closer and closer to 1. How did I get that? Where did that come from?
Seems reasonable to look at how those values of x impact both the numerator and denominator, the value in the numerator and the denominator. So
Okay.
x gets really, really large, the numerator is going to get really, really large.
Yes.
And likewise in the denominator. Now, the cool thing is that in your sort of simplified version,
Yes.
it's relatively easy for me to see that I have a power of 2 on the exponent for x, the largest sort of
Well,
power.
look up at the original function.
Oh, I'm sorry. Did I miss? Oh, I missed one. Looks like you've got
I've
Looks
got
like
an
you've
x,
got 4 actually. Yeah,
right?
sorry.
Good.
And same in the denominator. And so because I've got an x to the power 4 and an x to the power 4, all the others are going to fall away because
Yes,
those are going to take over. And so I see that I should have positive 1 in both directions, right? Uh,
correct.
because a negative, or well, because it's it's an even power, I'm going to have a positive over a positive, which is cool.
So what you've really done, I think, is you've taken a look at the ratio
Mm-hmm.
of the coefficients on the highest powers of x in both the numerator and the denominator, which happen to be the same here, x to the fourth and x to the fourth. Now, you might not see that, but give me just a little second here. I'm going to try to write this out just for the heck of it and just for completeness. I think when I multiplied all of this out, and maybe Tom or Vicky will check me on this, but I got an x to the fourth minus 5x cubed plus 6x squared plus 4x minus 8. All of that divided by x to the fourth plus 3x cubed plus, whoops, I'm sorry, that's a minus sign, 3x squared minus 11x minus 6. And Curtis, you're absolutely right. That as x increases without bound, the dominating terms here in this rational function are the x to the fourth terms. Because the largest power in the numerator and the denominator is the same, in order to find these horizontal asymptotes, we take a look at the ratio of those coefficients out in front, and both of them have a 1 there. Since these are even powers and those coefficients are positive, it's going to be going to 1 from both the left pardon me, as x increases without bound and as x decreases without bound. That's cool. I tried to put this all together. I know Tom and Vicky will do show you some of this with the calculator, but I produced this graph with Mathematica, and I tried to make sure I got all of the characteristics here that we discovered about this rational function. My dashed lines represent my asymptotes, so I have a vertical asymptote at x equal -3 and -1. I have a horizontal asymptote at y equal 1, and it might be a little hard to see, but there is indeed a hole right here at 2, 0 that we discovered. And I have a question for you, Curtis, and one that Tom may be able to answer with technology. You know, looking at this graph, it almost looks like the graph of this function goes down to that hole at x equal 2, and it almost looks like the values of f are negative for a while, and then come back up and get closer and closer to y equal 1. So analytically, I want to know why that can't happen. And then maybe Tom will do a little bit of zooming here in order to figure out whether that's true or not. Tom, I'll hand it over to you for a little calculator.
Okay. Great. I'll fire up my TI-84 and let me go ahead and share my screen. And hopefully that's coming up where you can see it.
Got it.
Okay,
Yep, got it.
fantastic. All right. So just
While
wanted to
Tom's doing that, I am just gonna hopefully somebody puts in the chat the answer to your question, Steve. I'm passing that one along.
Oh, okay.
I mean, I've got a response, but I don't want to steal the show.
Okay.
All right. Well, I'm going to go to the y equals menu and just go ahead and enter this function that Steve was working with. We'll take a look at it graphically. And first thing is, because it's a rational function, it's nicely written in that kind of fraction format. I'm going to take advantage of this fraction template. It's the alpha shift of that xt theta n key. And it gives us a vertical fraction there. And now I'm just going to go ahead and put in the numerator denominator of Steve's function here. So let's see, he had it in a nice factored form. And hopefully you all will yell at me if you see me make a typo here anywhere.
Looks good.
So far, so good. We'll see. Here we go. Great. And now we'll go down to the denominator and enter those factors. Oops, I think that's not what I wanted. There we go. X plus 1 squared. And then that's times x minus 2. And times x minus 3.
Good.
Plus 3.
Plus
X
3.
plus 3.
Yeah,
Thank you very
plus
much.
3.
Yep.
Yep.
Okay, there we go. All right. Now I wanted to go ahead and take the time to see how you could use that fraction template. It doesn't really take
Yes.
that much time to type in. I am going to, before I graph this, I am going to jump on a little bit of a soapbox here. Steve made it very important. This was the way the function was presented. And there's lots of textbooks, and this is kind of the convention in both AP pre-calculus and AP calculus is when you're given an expression for a function, unless you're told otherwise, the domain is going to be all the values that's defined for. And so that kind of first thing Steve did was analyze what the domain was. Now, if you simplify it, well, that new expression might be a little easier to deal with, but now you've got to keep that domain, okay?
Mhm.
Because if you pretend that, okay, this is my new function, and then start it over again, you might lose values or actually gain values that you had excluded from the domain before. And so, yeah, on that domain, that Steve, it's all the values except for -1, 2, and -3. except for those values, the two expressions do have exactly the same value, so you could use them interchangeably. But we want to be careful that once you simplify an expression, make sure you keep that original domain, because that's a key part. All right, I'll shut up there and let's take a look at the graph here, okay? I'm going to go ahead and use my usual favorite window, which is zoom decimal. Let's see what we get here for it. Might not have been the best window. We'll see. It's not too bad. We might want to perhaps zoom out a bit. Let's see what would happen if we zoomed out here. Let's see, we'll zoom out. And now I think I'm getting something that's starting to look a little bit more like part of the graph that Steve had, though we're just seeing just a little bit of that portion that's between the two asymptotes. All right. And I just wanted to point out, I'm going to go ahead and go back to my original picture, zoom decimal, and just wanted to trace over to, oh, look at that. Because I had that written in the vertical fraction form, notice how the y values are being reported here. They're actually being reported out as fractions. So when x is 0, y is 4/3. Let's see, Steve, I think he said something about a whole at 2, 0.
Yes, sir.
It looks to me like there's, the graph goes, let's check it out. Let's trace over there. And you can see all these various fractions that we're getting. Okay, I'm getting close, getting close.
Notice that they're all positive y values so far.
All positive y values. And now here's the drum roll, x equals 2.
Ta-da!
No y value at all. And there actually is a hole. A little bit hard to see that there is actually a missing, the graph is not connected through there. The reason it's hard to see is because it's right on the x-axis, and it's kind of filling in our visual. Now, Steve, your question was what, as we move past 2?
Yeah, it kind of looks like it goes negative, and then we'll aim towards that horizontal asymptote at y equal 1. I mean, it almost looks like those blue pixels are below the axis.
Yeah, it does, doesn't it? Let's go just 1 pixel past. Oh, it's still positive. Very small, but it is positive.
Yeah.
And staying positive, and now it looks like it's increasing and going to approach 1 again.
Yeah.
I did get one comment.
We're not real close to 1 yet.
No, we got a long ways to go.
We got a
Long way to go.
But Tom and Steve, I think it's so important that students realize that they may need to look at 2 or even 3 different windows with a function that has these different characteristics in order to really put together the things that they've come up with, where the location of the hole is, the locations of the asymptotes. So one picture, one graph doesn't show us everything we might need to know.
That's for sure the case. For sure the case in this one.
Yeah.
For sure. I did get one person gave a helpful hint.
Okay.
In the question about why it might appear that we go below the axes, even though it doesn't look like it based on Tom's graph now. That we traced a little bit, but why that might be, and they hinted that it might have something to do with the numerator. And I would argue that maybe we could look for other possibilities of 0 in the numerator.
Yeah.
So when I first graphed this, not with a calculator, it certainly looked to me like it went down and dipped down below the x-axis and then came back up. But analytically, why do we know that that can't happen? It's because we searched for zeros
And we only found one.
There aren't.
We only found one. We only found one possibility, and it happens to be a removable discontinuity, a hole in the graph.
Yeah.
Yeah.
Yeah. So it can't dip down and come back up.
Right.
Yeah.
Because if it did, we'd have to come back across the x-axis again.
There we go.
So Tom, if you could try this, you and Vicky have different. We all have different ways of doing this. But one of the things that I often ask my students is, well, what I really want you to produce on your calculator is a complete graph. Now, that might mean that I don't see every single little feature in great detail, but I'd kind of like to see a complete graph. So for example, in this window, I don't see anything going on between -3 and -1, and I can barely see a part of the graph off there to the top left.
Right.
So how do you go about, how would you recommend, Vicky, Tom, how would you recommend, and now that we know a little bit about this function, how do you recommend producing a complete graph?
Well, I think the Zoom that Tom did a few minutes ago got us started.
Okay.
But we needed a little more there. And I think what we needed to see from that Zoom, that we needed some lower Y, a lower Y min in order to see that part of the graph that was just a little teeny bit showing.
Okay. So
here's something I might try to do to get there is a Zoom fit that one could try, but keep in mind that this function has an asymptote, vertical asymptote, so we might get a really kind of weird window.
Yeah.
Okay.
But what I might do is I was tracing just pixel by pixel, but we could jump over any value on screen here. For example, if I typed in -1, because I might be looking at that expression and say, oh, it looks like the numerator is 0 at -1. What happens if I plug that in? Oops, no Y value at all. That's because that factor of x plus 1 is showing up also, actually 2 times in the denominator. But now I'm going to trace to the left, and I'm starting to get a sense for how big these values are, positive or negative. When I say big, I mean big in magnitude, absolute value. So
how far away from the x-axis they are.
Yeah, so this is, and you know what? This is kind of, I'm having to do some arithmetic to try to estimate, well, what is this number here? And it's not too bad, but it's, if I think of it as about a -1,000 over 20,
yeah,
and that's going to be about -50.
Mm-hmm.
Let me keep tracing. Well, that's not quite as good. That's close to -25-ish, right?
Mm-hmm.
And these are, okay. So that might make me think, well, maybe if I made -50 my Y min, I'd get a better looking graph. Okay. And Y max, well, let's see, all these values are negative right now. Let me jump over to where it's positive again, like maybe over to -4.
okay,
Oh, see 12 there. And let's see, it looks like it, well, let me trace actually. Well, these values are kind of hard to decipher. So, but in any case, I'm going to try the following. I'm going to go to the window, and I'm going to change my Y min to -50.
okay,
And I'm going to change my Y max to about 20, just for grins.
okay.
Yes, I'm not guaranteed this is going to give me a really good graph, but let's give it a shot and see what happens.
Okay. It's actually not too bad.
It's not bad. It's not bad. Okay.
Yeah.
Now you might be disconcerted. Now I didn't fool around with the X min, X max, and that's because all the important kind of cool points on this graph, the zeros and the holes and the asymptotes, were already in that window. So in terms of that kind of interesting behavior, it looked like our X range was just fine. It was the Y range that left something to be desired. And this is looking a lot better. If you're disconcerted with all these tick marks on the Y-axis, that's something we could have changed. I go to the window. That's what that X scale means. There's a tick mark. or hash mark every 1 unit on the x-axis. Well, that's not too bad. We're getting a lot of y because of the range being from -50 to 20. We're going to get a bunch of those. So why don't I change that to 10? So that means we'll have a hash mark every 10 units. Yeah, it doesn't look too bad.
It looks good. Yeah.
And you can still trace. So that's getting more closely. But notice what I did was I just kind of sampled,
Yeah.
to see, well, what kind of y values am I getting? And that's not going to be a guarantee, but we ended up doing a fairly nice job. There was one other thing I would like to show, and Curtis or Vicky might have a different tactic for this, but those trace values, when they came up as fractions for the y values, it's like if you're trying to figure out how big they are, you have to that. It makes it a little more challenging. At that point, we might have liked to have decimal values. So here's a real quick way you can make that happen. If you go back to your y equals menu, notice it's coming up y1, and my cursor is right in front of the fraction. I'm just going to type in 1.0 times that fraction. Now, that decimal number that I stuck in, when I multiply by 1, I don't change anything, but that will force it to trace in decimal form now. So if I now graph it again, and I turn on the trace now, notice that I'm getting decimal values. Mm-hmm. And I don't know if there's a slicker way to do that, but that's kind of been my go-to on both TI-84 and Nspire, for that matter. Is sometimes I'll just put in a factor of 1.0 to force it to do decimals for me. So,
Tom, right. I think if you
go ahead, Curtis.
I was just going to say, if you put the calculator in, I noticed that you've got it in auto.
In the modes? Is that where it would be?
If you just change that mode from auto to decimal, that's also another way to force decimal responses.
Down here under answers?
Down underneath the answers, I think that should also force your.
Okay, so if we had done decimal,
answer type. Right.
Okay.
So that will ignore sort of the fraction template, if you will, and just
override it, so to speak. Yeah,
not ignore it, I suppose. Override it is a better way to
I really like, though, what Tom did, because that's quick to just go into the Y1 and enter the 1.0 times. And I think it's a good thing to have pointed out to everyone that that's a possibility. There is one thing I'd like for you to do. I don't know what else you were planning here, but I'd like for you to go back to that original window that we didn't see the complete graph, but we did see a lot of the activity near the axis, near those values that were kind of important to us as undefined values and zeros that we located. This came up in the Facebook group this week, actually. So I'd like for you to graph the horizontal asymptote y equals 1.
Okay. So let's just go to our y equals.
Okay.
Let's graph y2 equal, said 2.
Yeah, said 2 and type 2. I do it all the time.
There we go. That's what we think the horizontal asymptote.
Yeah. I mean, we could change it to a dash line or something, but that's
I was just going to say, you want to get fancy and make it a dash line.
Dash line. The question came up, someone had a graph that crossed the horizontal asymptote, and they were kind of like, wait, can that happen? Well, yeah, we're seeing a fantastic example of it here, but they had this notion that and I don't know if it happens in the earlier math classes or what, but you can't cross, and they just collectively say asymptotes when they actually mean only vertical asymptotes, because we can definitely, we see it here, we can cross a horizontal asymptote, but that usually happens kind of in the, where the important stuff's going on, which is kind of the screen we're looking at now. But then we have to understand that that horizontal asymptote is an end behavior asymptote, and that we're looking at the extremes as x approaches positive infinity and negative infinity, and that's what we're describing with the horizontal asymptote.
Tom, there may be to actually go along with Vicky's point here. There may be a nice tool tip or tech tip here, also for exploring graphs of this nature, where you've really kind of got sort of the range values, the y values that you're interested in this picture, or maybe okay, maybe that -50 down there hanging out down below. But really, we're going to talk about end behavior as we go. X goes to really, really large positive or really, really far in the negative direction as well. And you don't really need to zoom a whole lot vertically, but you need to maybe be able to zoom out on just the x-axis. That might be an interesting skill to be able to demonstrate here, to that fact that you can change the zoom out factors
Zoom horizontally.
on
Yeah.
just one axis at a time. And this could be a cool demo of that, particularly in the fact that, yeah, we do see that we cross this horizontal asymptote, but then when you zoom way out, you can see that you do then approach that horizontal asymptote as x gets large magnitude.
Shall we go ahead and do it?
Sure.
Yeah, I think you ought to walk us through that.
Absolutely.
I'm going to go to the zoom menu here, and rather than choose one of these kind of special windows in the zoom or the zoom in, zoom out, I'm going to go to memory. And if we go down to the bottom there, the set factors, these are the default factors that you would zoom in or zoom out by if you use those options. So if you zoom in, it'll zoom in by factors of 4 in both directions, x and y. If you zoom out, it'll zoom out by factors of 4. Well, if I want to leave my y range alone, not mess with it at all, but zoom out just horizontally in the x direction, what I can do is change the y factor to 1. Okay. Now that's not going to change my y range at all when I do things like zooming out or zooming in. And just while we're here, I'm going to increase the x factor up to 10. Okay. So what does this look like? Well, I'm going to go to zoom, and I'm going to do a zoom out, because we're interested in what happens as the end behavior as we go out further and further from the origin.
Mm-hmm.
Okay, there we go. So here's a zoom out, and there you see that effect on those hash marks. And now we're seeing that asymptotic behavior toward that asymptote y equals 1. In fact, if you were to zoom out again, which at this point, all I have to do is hit enter again because it's kind of prepped. It's actually my blue graph, the original function graph, almost looked like the asymptote graph until we got closer to 0 where the action was. By the way, our trace values, if I was to trace, notice what the x values increment by. We're going by tens now. That's because I zoomed out by a factor of 10 twice. Okay, so it's going 10, 20, 30. And you can see those y values getting closer and closer to 1. All right. Let me go back.
I'm really glad you did that. I
Okay.
think that's real important for the students to see. And I mean, and just the fact that this particular function dipped down to that hole and then came back up toward the horizontal asymptote. I always used to say in my class, from the bottom of it is I think that's just an important feature of a graph that students can begin to understand. This can happen, and be aware of it.
Yeah, and in fact, if we zoomed out just one more time,
it's just going to look like the other graph.
now I might
there's a little blip right there.
There's a little blip, but not much.
Yeah.
I'm going to do it again.
Uh-oh.
There's the blue graph. Whoa, we can just barely see something going on near the origin. And just for
So
one last time.
Uh-oh, you got Tom carried away now.
now yeah,
Well, now
I've
I'm
really
having trouble
I've
distinguishing
taken him
between-
off. Now he's going off without bound. We we
Yeah,
we got some
Vicky,
good comments in the chat too. One thing to note, Karen Camp chimed in and did mention that the Zoom Fit should show that -50 section down there in the bottom. So when you had that Zoom decimal window that was kind of nice, important stuff, and then using Zoom Fit right afterwards, you should get that smaller asymptote. So I think that's good.
that's
Some
a
people
nice
are
point. I think
that
it
Thomas,
probably depends on how close
yeah,
your pixels are to an asymptote, whether you
Right.
might get some
right.
outlandish.
Based on your window, your domain, that might or might not work, depends on some things. Some folks are talking about how much fun it appears Tom is having with the zoom out.
We all
But then
are.
I noted lots of folks kind of remembering different ways that their Algebra 1 teachers have, or Algebra 2 teachers rather, have commented on this idea. And the last one being, I remember a friend joking that asymptotes stay in shape because they approach their limits. And so,
Ugh.
Ooh.
and on that note, maybe I'll turn it back over.
And to clean
And
things
Steve,
up here, I've gone ahead and set
Vicky better wrangle us in here and get us back on track.
Well, Tom,
Okay.
I wanted to, before I go to the next problem, just wanted to expand on something that Vicky mentioned a moment ago. Can the graph have a function actually cross its horizontal asymptote or a horizontal asymptote? And the answer is, of course, it can, but not only can it cross it once, but it can actually cross it infinitely many times. You know, the classic example at least in calculus is, we have this graph that comes down and wobbles like this and gets closer and closer and closer to that horizontal asymptote as x increases without bound. So not only can it cross it once, but it can cross it many times. And the second thing, you don't have to do this, Tom, but Curtis hinted at this a minute ago about making that red line, that horizontal asymptote dash, to really make it look like a horizontal asymptote. But one thing that's often lost that I always have to search for is, what if I wanted to put in a vertical line in my graph?
Okay.
How do I add a vertical line to that graph screen?
Well, Curtis will know the answer to that.
I know the answer to this. Well, there's probably multiple ways you can do it.
Okay.
But students will probably like to be able to add a vertical line in the form of x equals something.
Correct.
That tends to be the way we want to be able to do it.
So can you
And
do
if that
that
is the
easily?
case,
Can
the
we do
best
that?
way to do that is to use the application inequalities or inequals. You go down here to number 7 there, inequals underneath that menu, and enter that. I know some teachers actually turn the inequality app on and leave it on all the time. Go ahead and quit the transform app, Tom, number 2 there. And then go back to press any key. I always have trouble finding the any key, by the way. And if you go up to, you see up in the upper left-hand corner, there's this x equals now that shows up as a part of the inequalities app.
Yes.
Now you can press enter there, and here you can type in inequalities. Actually, if you'd like to be able to shade left or right some domain values, that's also helpful. But in this case, Tom can type in some of those vertical asymptotes that we know that we have in this graph, x equals -3. And then when you draw the graph, you'll have a line, a vertical line at x equals -3. You should be able to put that in there.
There we go.
And now we'll have those. Well, we'll have one blue line and one red line. That's nice. Of course, you could make those dashed lines and
Gotcha.
do some of the formatting if you
So
like.
to make those dashed lines, Curtis, would I go to this area?
So go arrow back up to x equals there and edit those.
Right.
If you arrow to the left there, you should be able to change that
Yeah.
symbol. Oops, down, press enter.
Hit enter.
There you go. Select
The
it.
style is what we're after.
When you change the style there, you should be able to change that style to a dotted line. Oh, no, it's only a solid line.
Oh, it's only
Okay.
solid. Interesting.
Yeah. Well, it's because you have x equals, there isn't a x not equal to form there.
But we could go back and change the horizontal if we wanted to just show them how
Right.
that works.
Yeah.
Okay.
So go to y equal. Is that correct?
On a asymptote. I'll arrow over here, hit enter.
Yep.
And now see if we've got a style choice of dotted.
It might not because you're in the app, the inequalities app too. I don't know.
Oh, okay.
So there's another way to do this. Question came up, could we do it without the inequalities app? There's a couple of ways you can do it. Probably the best way to do it is to use the draw menu.
Yes.
Karen mentions it in the chat. You can use the draw menu to draw vertical lines.
And for
That,
what it's worth, I did change the style here a little bit. I made the horizontal asymptote and one of the vertical asymptotes thinner.
Mhm.
actually thinner.
So it is
Mhm.
actually is noticeable at least.
Yep.
So
Yep.
the other alternative was going to the draw menu.
The draw menu. Mhm.
And there's
So if you go to
the
draw,
vertical.
you can
Vertical,
draw
yeah.
vertical.
Okay.
And then you can put that in there. You might note some
And then
other
you could arrow over to wherever you wanted a vertical
Mhm.
line.
right, and then you can change the style.
So as a student, I probably wouldn't go to all this trouble to produce a graph, but this is very helpful for a teacher that might
Absolutely.
want to do a capture of this image to put on like a worksheet or a quiz or a test or something like that.
Yep. Absolutely. Very
So
cool.
these triangular style lines, what are those?
It's going to be shading
Shading.
left and right.
Oh, right. Okay. I'm still not seeing dotted really as an option.
I didn't see dotted there either.
I still
it
think
looks
it might
like
be because
thin
we're
is
in that
it?
app,
Oh,
but I don't
because
know.
we're
I'll
in the-
investigate that.
Yeah.
I'll investigate that while you're playing. I'll come back and give you.
Well, I think I probably should bail out here and turn it back over to Steve.
Okay.
Okay.
Yeah, let's look at another exciting problem.
All right. All right. Here we go. This is problem 2. Curtis, can we stay on till about 10 o'clock tonight?
It sounds like we better in order to get to all these.
All right. Well, problem 2, I understand some of Tom's favorite kind of problems, and I apologize. I didn't group a lot of this information together in a nice way. But anyway, what we want to do is kind of work backwards here. We want to see if we can find a rational function that satisfies the given conditions. And then when we have one, we want to sketch a graph of this function in order to confirm or illustrate those conditions. So I'm going to work through these a little bit at a time. I'm going to try to work between the conditions and my final answer down here, see if I can make everything correspond. Let's see. The limit as x goes to infinity of f of x is equal to 1. The limit as x goes to minus infinity. Let's take a look at both of those conditions, first of all. Given
We
what
kind of have a hint from the last example of what we might need to happen.
we do indeed. What is that, Curtis?
Sorry, I was
He's
distracted by the
making
chat.
dotted
Hold on.
lines.
Oh, man.
I
Well,
was distracted by the chat. There was a question I missed that we didn't cover, but Mark Crowley covered for us, so
all right.
we're good.
Well, what does this mean here? As x increases without bound, the function's going to 1. As x decreases without bound, the function is also going to 1. It says we have a horizontal asymptote at y equal 1 again, doesn't it? Now, we're trying to produce a rational function. We're trying to produce the actual formula, the equation here. And so what does that say here about the polynomial in the numerator and the polynomial in the denominator? What's got to happen?
They've got the same they're the same degree polynomial.
Okay, and the ratio of the coefficients
Is 1.
beautiful. All right. Okay. So we've handled that. All right. We've handled those two. Let's take a look at these two together. The limit as x goes to minus 2 from the left. I apologize, Vicky, help me on this a little bit. I know we're testing, or pardon me, we're trying to teach good notational fluency. Would students in pre-calc be expected to know that kind of notation?
Yes,
Okay.
yes.
The
They
limit
need
is
to be able to describe the behavior on either side of a vertical asymptote using a limit expression. And
okay.
that's exactly what you have.
Okay, good. So the limit as x goes to -2 from the left of f of x is equal to -infinity. The limit as x goes to -2 from the right of f of x is equal to +infinity. I apologize, a little aside here. I was giving a presentation, something like this, a while ago, and I wrote these two limits down, very similar to this, these two one-sided limits, and I wrote them like this, the way I think is traditional, with the plus signs as superscript and the minus sign as a superscript. And a teacher raised their hand and said, "Oh, well, my students like to use arrows. Can they use arrows? Is that okay?" And I said, could you just teach them to use the usual notation rather than the arrows? I don't think they like that answer, but you know, we get these, Tom and Vicky, Curtis, we get these questions all the time. You know, my student uses this kind of notation. Is that okay? My student uses MVT rather than writing out mean value theorem. Or, you know, my student writes INC rather than increasing. Is that okay? And, you know, my pat sort of blunt response is, could you do it the right way? You know, I know you're under the pressure of a high stakes exam. I get that. But you know what? We're teaching notational fluency. We want students to write things correctly mathematically. All
And
right.
why take a chance? Why take a
After,
chance? Yeah.
absolutely. After all of that, what are these two conditions telling me? Holy Toledo, can we interpret that? Tom knows that this is one of my pet peeves, and that is being able to translate the mathematics into words. Can I translate what this is really telling me into sort of a sentence, or conceptually what's going on there? Any chance, Curtis? Can you tell me what those two expressions are telling me about the graph of this function?
The limit, sorry, I was not
Yeah,
paying attention.
we're
I was
gonna
trying to
ban you from
answer.
social media here, Curtis.
No, don't ban me from social media. I'm trying to answer questions.
What are
How
those
about
two?
how about I'll help a little bit,
All right,
because
Help
go
I
me
ahead.
out,
think one of the
Vicky.
things that's important is you've got a computer generated graph down there. I
Yep,
think what we would probably advise students to do is sort of begin to hand sketch what these limits and ideas that are given are telling them, so that it
absolutely.
becomes clear that they are seeing that vertical asymptote. That's what those two limits are telling us, that we've got a vertical asymptote at x equals -2. But if they sketched those approaching positive infinity, negative infinity on either side of -2, I think that would make it clearer to them as they were working on this problem.
I
So
love the sketch as you go kind of thing here, just sketching out what that means as you get close to that. I think that's a really smart way
so
of
here's part
just
of my
getting
sketch.
a
There it is.
general idea
Yeah,
Yeah.
of what's going on
there you
here.
go,
Yeah.
like
So,
that.
so I have another question for you then, Curtis. One of these limits is -infinity.
He just never learns, does he?
One's +infinity. What does that tell me about the rational function when I go to construct this?
One's plus infinity and one's minus infinity.
Yeah, what does
Uh,
that tell
that
me?
I don't have a squared term in the denominator around that
Very
-2,
good,
or
very good.
sorry,
So that term, that linear factor x plus 2, I think maybe a
an
more general way
odd.
to say this, but correct me, yeah, it has to be odd, doesn't it? Right? And there can't be any cancellation that makes that even. Very good. Excellent. Okay, after that, what does this tell me? F of -5 is equal to 0. What does that say in words? Vicky, I guess you better help Curtis here today. He's back to social media.
And we have a 0 of the function there. Well, not a 0,
Sure.
I'm sorry. We have a place on the y-axis where, what am I looking at? X of -5 is
0. Sure.
0. Yeah,
Yeah,
there it is right there. We do have an x-intercept right there.
sure. So if I were to continue under this scenario and try to continue to draw this curve, I guess I can see it coming up and hitting that
Mhm.
-5. Um, I don't see any other information up there about suggesting there are any other zeros there. I
Correct.
know I have already drawn in my horizontal asymptote at y=1, so I can expect that this graph goes up and approaches that horizontal asymptote like that.
Right.
There might be
Because
some,
and something else to think about, I'm sure you could like create other functions that meet the criteria here, but I
absolutely.
don't think we want to
Absolutely.
input more difficulty into the question than we need to. We need to kind of take it as is and what we can have
Minimalistic.
here.
Yep,
Yes,
minimalistic.
yes,
That is absolutely
minimalistic
correct.
there.
Yep. And I think the last piece of information or characteristic I had up here was that the graph of f has a hole at x minus,
Mhm.
pardon me, at x=2. I apologize, it's kind of small on my graph, but there it is.
It
And so
is
here comes my
fine.
curve down there, and there's a hole, and there we go. Can I produce this rational expression? Well, let's see. Since there's a hole at at x=2, I want to be able to cancel out those factors. So minimalistic, I have an x-2 in the numerator and an x-2 in the denominator.
Right?
I know that at -5, I have a 0. So I need
Correct.
a +5 in the numerator. I know I have a vertical asymptote at -2. And I know that it goes off to plus infinity on one side, minus infinity on the other. I'm going to put that x+2 to the first power, an odd power down there. Now, one more thing that I want to check is to make sure that both the numerator and the denominator have the same degree, and they do. The degree is
Mhm.
2. And without multiplying anything out, although I could, I think it's pretty easy to see that the leading coefficient in the numerator, pardon me, the leading power of x in the numerator and the denominator is x squared, and both of those terms have 1 as a coefficient. So indeed, the ratio of those leading coefficients is 1, and that gives me my horizontal asymptote at y=1. Hey, cool, pretty good. Are there other ways to write this function and satisfy these conditions, Vicky? You're
Yeah.
absolutely right. And we might leave that as sort of a challenge. Can you produce another rational function that has these same characteristics and graph that
I
one?
think that'd be a great challenge.
I like that. Tom, can I look at part B here before you do anything else with technology?
Sure, Steve. Oh, I would like to just
If you do it fast, Steve.
Okay.
I'm going to throw in though one real quick plug here, Steve. For
Okay, sure. Go ahead.
There's lots of textbooks that they have tons and tons of exercises where you're given a function like you've got here, and you're asked to find the y-intercepts, the x-intercepts, vertical asymptotes, horizontal asymptotes, zeros, and location of any holes if there are any.
Like our first problem.
What you've done here,
Yeah.
though, is my pet name is you've done the Jeopardy version of this.
Uh-huh.
You've given the analysis instead, and then asked students to come up with a function. And I think that it's just a really cool way to ask it, and it get at a really robust understanding. So kudos
Agreed.
on this problem. So back to you.
Okay, I'll try part B, although I'm a little worried with the mention of Jeopardy that Curtis is going to start singing that song. But
Not going to start singing the song because I want to make sure Tom has time to demonstrate one last cool tech thing here.
Okay, let's see here. The limit as x goes to infinity is infinity. Oh no, the limit as x goes to minus infinity is minus infinity. Holy Toledo, what does that tell me here? What does that tell me about my rational expression? Oh, well, wait a minute. I'll answer part of that. There are no horizontal asymptotes. But what does that tell me about this rational expression when I go to construct this? Well, we'll leave that as an open question for a moment. What about the limit as x goes to -3 from the left, limit as x goes to -3 from the right? Well, one's infinity, one's minus infinity. Okay, as in the previous problem, I believe we have a vertical asymptote at x = -3, and because it's minus infinity on one side plus infinity on the other, I'm going to go with a minimal rational function here with an x + 3 in the denominator. There it is. And as Vicky suggested, maybe I should start drawing this. So let's see. Kind of hard to see on my graph, but it's coming down like this, and it's going down like that, going down to minus infinity as I approach -3 from the left-hand side. How about this one? The limit as x goes to 5 from the left, the limit as x goes to 5 from the right. Minus infinity and plus infinity. Well, son of a gun, I have another vertical asymptote. I have a factor of x minus 1 to the first power because it's minus infinity on one side, plus infinity on the other. I'll start to draw part of that. I've got my dashed lines in there already. You don't see a horizontal one in there. I don't think there is one. There is no horizontal asymptote. I have, let's see, what do I have here? I have 2 zeros.
Yep.
F of minus 6 is 0, and f of minus 2 is 0. So here comes the function. It crosses right there and goes down to minus infinity. Here comes this function up closer and closer to the x-axis, crosses it at minus 6. We know it doesn't come back down. Well, in this minimal approach, because there are no other zeros given to me. What does my rational expression have to look like? Well, let's see. I've got the x plus 3, I've got the x plus 5, minus 5, excuse me, in the denominator, because I've got vertical asymptotes there. I don't want anything canceling out with those two. I've got the x plus 2 up there in the numerator to give me a 0 at minus 2. I've got an x plus 6 up there in the numerator to give me a 0 at minus 6. Aha! But why did I put the square on there? I wonder why. And there's that lonely 10 in the denominator. Well, the reason that I put that there just so that I could make this graph more visible. Otherwise, the values were really large. So that's not playing a role in here. That didn't follow from any of these characteristics. But why is the x plus 6 squared? That was a choice I made. Why did I put that there?
Did the x plus 6 have to be the one that's squared?
Well, does it? Why did I have to square one of those terms? Curtis.
Well, it goes back to something that is not real visible to me on the graph that you do have, because we probably need to see a little more of
We
it.
need to see more, don't we, Vicky?
We
Absolutely.
do.
What
Because
characteristics?
those first
the
two
end
limits,
behavior.
the end behavior is not a horizontal asymptote. So the
Right.
degree in the numerator has to be higher than the degree in the denominator.
Correct. Absolutely. And
Yay.
it's hard to see on my graph, but I believe what's happening here is this function just kisses that x equal minus 6, and then it comes back
Comes
down.
back down and down, down, down.
And
Yes.
over here, as x increases without bound, notice the function has to go off to infinity, and indeed it does curve back up and go up like that.
Yep.
Beautiful. Tom, I'll hand it over to you for one last piece of technology.
Okay.
Tom, will you go back to part A real quick?
Okay.
Draw the graph of that
He might just say no.
He might.
And draw the graph of that one on a Zoom decimal window, and just show us what we end up seeing on that one.
Okay.
I believe it was the fraction x plus the quantity x plus 5 times x minus 2. Was that right?
X plus 5 times x minus 2 in the numerator.
And
X
then x
plus
minus 2 and x plus 2 in the denominator.
The denominator, yep.
And go ahead and graph that on a nice Zoom decimal window.
All right. Almost got it here. I think I didn't make any typos here as far
Don't
as
see any typos.
Looks good.
So let's do a Zoom decimal window and get a look at what we've got. Oh, not bad. Oh, and I love what's happening at x equal 2 visually.
Hey,
Yes.
pretty cool.
Tom, is your calculator broken? What's going on? Something is funky going on at x equals 2.
And these folks have heard this story before, but this happened the very first day I ever used graphing calculators in the class. I had students graphing a rational function, and it had a removable discontinuity in it. And one of the students was surprised and said, why does my graph have a hole in it? And I was sold on graphing calculators from that moment. So I said, wow, they've personalized the experience. They said, my graph. And they were interested in it. They were wondering what is causing this to happen? Is it a calculator defect or is there something else happening? And it was a great entry point to a discussion of limits and behavior functions that was more powerful than anything I've done with the chalkboard before. So, and this is cool. Happening, you actually see the hole there. You don't have the x-axis in the way this time.
Yeah.
Pretty cool.
Right.
Yeah, I just think this is a big value add in terms of just really driving home that idea of we have a value at which this graph is undefined, indeterminate. We don't know what to do with that removable discontinuity. It's just not there.
Just not there, yeah. And the trace confirms that. It says, no, just don't have a Y value there.
So I'm just going to speak to the students that are on right now. So they've been using some big words like removable discontinuity. You'll learn about that in calculus. We just kind of call it a hole in pre-calculus. You're okay.
Yeah, I keep calling it removable discontinuity.
It's okay. They'll figure out what that is. They'll have a better understanding of it in calculus next year because they have experienced holes in their graphs.
That's right.
I think, Tom, you mentioned this already, but this is also an excellent visualization of this idea of a limit and what's going on as X approaches 2 from both the left and the right in this case. Now, that may not be something that you would do in pre-calculus, but that's something you could talk a little bit about and think a little bit about. Jeepers, what's happening to the value of this function Y as X approaches 2?
Steve, they do need to be able to write a limit statement as the X's approach the hole from the left and the right. So you are alluding to that by, thinking about the graphical, what's actually happening. And Tom, you could go in and show them trace and show them how those values are approaching 2 from either side also.
Yeah.
Nope, you're in fraction form too.
They're in fraction form. 23/13.
That's getting pretty close to 2.
71/41. Yeah.
So, Tom, before we quit this, you are in a Zoom decimal window and you're tracing by, I believe it's 0.1s.
Right.
Is there a quick way to trace by 0.01s?
Or, what we could just do is just evaluate close to 2. For example, I could just type in 2.001.
Okay.
I think that's quicker, honestly.
Okay.
And I get.
Gotcha.
Now I look at that and it's in fraction form. I can see that looks a lot like 7/4. Very, very.
Yeah, sure does.
And if I put in 1.999, just a little bit to the left,
Uh-huh.
that one's a little bit harder to, but
yeah.
But you gave us a great way that we could be looking at the decimal values by one little quick change in that Y equals. So that can help a lot
too. 1.0 in there.
Yeah.
Go back to the graph. Whoops. What did I? I think I tried to do it too fast.
Yeah.
Oh, I forgot to put in the multiplication symbol. There we go. Graph. Trace. And then we could put in 1.999 here. Something pretty darn close to 1.75.
Sure is.
We said 7/4 before, looked like.
Yeah.
Yep. Pretty cool.
And so I think that, Steve, is a way, rather than change the factors.
Yes.
The main thing is just plug in values closer and closer.
Sure.
From both sides, and see if you can see it closing in on a picture.
Yep. Gotcha. Okay. Thanks, Tom.
Okay, let me stop the share there.
Thanks, Curtis. Very good.
I like it. Well, this was a fun session. I know I had a good time, even though Steve kept asking me questions while I was distracted. Got saved by the chat a couple times, so that was great. Love having teachers and students on. I love also having just interaction among the four of us and the teachers and students on the chat. This is a lot of fun. So we will be back here in roughly a month to kind of give another look at periodic. Is that right? I can't remember
We're
where we're
doing
headed. Where we
some
headed next?
regressions and
Yeah.
some
Oh, we're doing some
We're going to look
regression.
at some modeling.
That's
Yeah.
right.
modeling.
And
We're
Yeah.
looking
we
at
hope,
modeling.
we may get back to the free response question. Is it number 2, Vicky?
Number
It's
2
number
that we
2.
didn't get
Get
to
back to that. Yep.
earlier. That's correct. So see, that's it. I've got too many of these things going on. So we'll be doing that in about 4 weeks. Looking forward to that. Teachers, I put my email in the chat. Please reach out to me for professional development hours. I'll send you a link to that. Otherwise, I will shut us down for the evening. Thanks very much.
Thanks, everybody.
Thanks, Chris.